Welcome to the second part of our discussion about experimental design. In the last topic we concentrated on setting the foundations for this, including exploring the importance of randomization and replication, the incorporation of a control and what a placebo was, and we looked at the simplest possible experimental design technique, which is a completely randomized design where our experimental system is divided into equally sized experimental units. They might be individual people or they may be plots in a paddock, and then we randomly sample within these plots a certain number of these plots, which are selected randomly, probably a better way of putting it. This week we'll look at examples where we can't just divide up the entire area into identical experimental units and randomly sample within them. We need to break up the overall area into smaller subsets or areas and then randomly sample within those. This is called blocking, and we'll finish by looking at a really neat version of blocking called the Latin square. So the key property of a good experiment, an experiment that has been designed well, compares the response of an experimental unit to another treatment and a control, or simply just a control. But we're always seeking to compare, and we make sure that when we are setting up this comparison between a number of treatments or a single treatment and a control, making sure we always have a control, is we make sure we have randomization so that any individual experimental unit is equally likely to be chosen, and we replicate. So we have numerous examples of each treatment. So then we can start getting a pattern. We can't generate a mean if we simply have the one value. And here we have the old favourite that always comes up at this point in a statistics and experimental design course, with the dartboard metaphor. And it's actually quite a good one when discussing both bias as well as the difference between population and sample mean, as well as standard deviation. If we look at the top left dartboard again, we see a tight grouping of, in this case, darts. Nice tight grouping, which means if this was a data set, the values would have a low standard deviation because there's not a lot of spread. And remember, standard deviation is a measure of spread. However, the sample mean that we've come up for, in this case attempting to estimate the true mean, which in this case is the bullseye itself, is off. There's been a bias such that our data points are found wide of the mark. So even though we've got low variation, we've got good precision, we'd have low accuracy. Accuracy means our sample mean is not a good estimate of the true mean. It's found away from the true mean. They're very precise though, in that they're all found closely together. The same thing occurs in the bottom right, but here we have good accuracy and good precision. Precision because all our darts have landed in the same area, and accuracy because they've landed in the right spot. So in this case our standard deviation would be low, and our sample mean would be a good estimate of the true mean because there it is, found in the middle. We have the converse on top, where we have low precision but we have high accuracy. We have low precision because our darts are spread across the dartboard. However, if you've got the mean dart position, they sort of come together in the middle. So we actually have a precise estimation of the true mean in this case. Whereas in the bottom left we have poor accuracy and poor precision. Our darts are spread out and they also won't be able to estimate the true mean well. So following on from my discussion in the previous slide, the question would be, if these were data points rather than darts, which of these would have the lowest standard deviation? So which one would have the lowest amount of spread? And as discussed before, that would be the top left and the bottom right. The numbers are closest together, so the average difference between each data point and the mean would be lowest. Next question is, which would have the smallest difference between the true mean and the sample mean? Well, again, as discussed before, they would be the two right-hand dartboards. Both of them, the mean is found pretty much in the middle of the dartboard. In the top right, there's more spread, but if you evened out those data points, they'd come out towards the middle. So if the middle, the bullseye, represents the true mean, then both of these would be the best estimate of the true mean. Therefore, the sample mean and the true mean would be closest. So here again we have the completely randomized design, CRD, the simplest possible design we can have. And as with this slide, as with all the others, for ease of visualization, we show examples which look like a paddock, which has been divided up into plots or experimental units. So if this was a paddock here with 4 sides, then the experimental units would just be small, evenly sized patches of that paddock for which we'd apply a treatment, say a fertilizer treatment. However, it could also represent people in a particular group. So it might be students in a class rather than plots on the ground. It can be anything really, but for the ease of this discussion, we'll keep it to the experimental units, to generally plots in a paddock. So in a completely randomized design, we just divide up the entire experimental area, say our agricultural system, the paddock, into evenly sized plots, and then we apply a treatment to randomly selected plots within that. And remember, to be randomized, each experimental unit has to be equally likely to be chosen as any others. For a completely randomized design, we have to make sure that the experimental area is homogeneous, it's environmentally the same. Otherwise, we may accidentally, even though we're using random processes, we may accidentally or randomly get an over-representation of plots in an area which might be drier or may receive more grazing. And that would bias our results. It would take the sample mean away from the true mean. If there is too much heterogeneity, we need to use blocking, which we'll explore here. So we use blocking when we don't have an homogeneous group of experimental units. In the case of, let's say, if we're using animals or humans as our experimental units, or if we don't have an homogeneous environment, if we're using a physical landscape to experiment on. So an example might be, we want to find out the average IQ of school students. If we randomly selected students from a school, we may by random select students in grade 5 and 6 who haven't fully developed. And therefore, we may underestimate the true mean IQ. Whereas what we might do to get a more valid result would be to randomly select or randomly sample students in each year group or small bands of year groups, so maybe grade 5 and grade 6, grade 7 and grade 8, so on and so forth. And then randomly sample within those. Even though we're blocking, we still need to randomly sample within each block. This blocking is one method we have for reducing confounding variables, which are variables we can't account for within our experiment and may bias our result. So here's a classic and simplified example of a block design. Let's say the top of this figure here we have a paddock with 4 different types of animals, here represented by different shapes. If we randomly sampled, say, fur length of these animals, if we randomly, by chance, had an over-representation of horses in our sampling, so we couldn't, so let's say we couldn't sample all the animals in this paddock, we could only take a subset, which would be very normal. And then by chance, using random methods, we had an over-representation of horses in our sample, then we would bias the average fur length of the animals in this paddock by that of horses, which might not be representative because we may have, say, sheep in this paddock with longer hair or wool. So what we might do instead is randomly sample within each group of animals. So we block for animal type, and then again we make sure we randomly sample within each block. So when I say randomly sample, this random sampling or data collection would occur after we've applied certain treatments to the experiment. So we may not just be going, okay, we might not just be doing an observational study where we go in there and measure hair length. We may actually want to look at the effect of a certain ointment on hair length. So we may apply this treatment to random individuals within each block and then measure its effect. That would be an experimental study. So an observational study would be dividing up the experimental units into blocks and then observing a variable. An experimental study would be dividing up our experimental units into blocks and then applying treatments randomly to experimental units within each block. So the beauty of blocking is that we essentially get more bang for our experimental buck. As in a normal experiment, we have factors, which are the treatments in which we're studying the effect of. However, with blocking, we get to monitor the effect of whatever we're blocking as well. Let's see this in action here in this example. Here we have a paddock which is divided up into 4 rows of 4 experimental units. And to each experimental unit, we wish to study the effect of 4 different treatments. Treatment A, B, C, and D. Let's say it's fertilizers. And these experimental units are areas of a paddock. One way we could do this is to randomly assign the different fertilizers to experimental units within this paddock, so the 16 experimental units. So, and we do that evenly, because why not? And we always try and balance our experiments if we can. So we'd find 4 random experimental units for each fertilizer. However, this is not an environmentally homogeneous area. In this case, there's a water gradient. It goes from low water at the top to high water at the bottom. So if we just randomly assign treatments, fertilizer A may be overrepresented in the high water area. That extra water may make, let's say we're measuring the variable of plant height, it may make the plants higher, which has got nothing to do with the extra fertilizer, but everything to do with the water. So instead what we do is try to make sure there's an equal representation of each treatment along this environmental gradient. So what I've done is divide this paddock up into 4 rows, and each treatment is found in an experimental unit within each row. Within each row, which I'll now call a block, I've randomly assigned that treatment to one of the experimental units. So now we have one of all 4 treatments in the low water level area, 4 in the high water level area, and in the different levels in between. And now, as I started off saying, not only can we compare the effect of each fertilizer, but we can also have a look at what effect water's having on whatever variables we're measuring as well. In special cases, we have what's called paired designs, where each block has 2 experimental units. And normally these 2 experimental units are perfect for a direct comparison. So for example, twin studies. We have 2 nearly genetically identical humans. And so what they do in a pair study here is they'll look at the effect of one treatment on one of the twins and one on the other. Now, because it's rare that you get human ethics approval to do actual experimentation on one twin and the other, often these are observational studies. So a recent one was, what was the effect if one twin drank alcohol and the other decided not to? So they found twins which fitted into each of these categories and then compared the 2 twins. You do get different experimental treatments applied to non-human subjects. So sheep are a good example who have lots of twins. So there's often paired studies in sheep looking at the effect of certain treatments on one twin and not the other. So here's the classic progression of experimental design when we are blocking. In this case, we're trying to look at the effect of effectiveness or response to 3 different advertisements. So the first step, which is a little bit blurry on the left, is determining whether or not to block or not. And in this case, the experimenters decided blocking was appropriate because they thought that maybe gender would play a role in how someone would respond to these adverts. So they determined some blocks and they went male and female. So the next step is to find your subjects. So they found, let's say, 300 subjects. Then they divide this group of subjects, and remember subjects are human experimental units, into the 2 blocks, male and female. And then they randomly assigned members of each block to a group, and each group watched a particular advert. And then they compared the reactions between these groups within each block. And then they could get an overall effect of the adverts, and they can also look at the difference between male and female responses to these adverts. So here's that more bang for your buck when you do block. So blocking seems easy, but it's important that we sit down before any experiment and really think about how we're going to do it. Because if we do it the wrong way, we lose all its value. Here's a pretty simple example of where blocking's gone wrong. We have a moisture gradient, as before, from top to bottom. If instead of choosing rows to block, such that each treatment could be found randomly within each zone of moisture, what if instead we blocked in columns from left to right? All the value of the blocking is gone because we couldn't make sure that we had an equal representation of each treatment in each moisture gradient area. So here's a real world example which shows the value of blocking, but also how we can't kid ourselves that blocking is always in nice square areas, uniform areas. It's not always that way. Here's a classic frost study where we have a crop in a paddock which has encountered a frost event. And we want to measure what's the average damage from this frost across this paddock. Well, if we randomly found plots to measure the average amount of frost across this paddock, it wouldn't work because we don't have homogeneous frost damage. If you can see in the background, or sort of the midground there, we have a weed infestation in this paddock. And these weeds have the effect to insulate the warmth from the soil away from the frost. So normally if there's bare earth, the soil will actually emit heat, which reduces the effect of the frost. If there's a layer of weeds there, that actually forms a buffer zone between the warm soil and the frost. So frost damage is worse. And you can see that in the midground there, the brown plants, due to the effect of the frost. So instead, in this case, we'd need to block for areas with weeds and areas with no weeds, and then randomly find plots within those areas to sample the amount of frost damage. So using a random number table, we can assign treatments to experimental units in 2 different ways. The first thing we could do is assign a number to each plot and then work from one treatment to the next sequentially and assign a plot to that treatment. So let's say the first treatment, we have 5 treatments, A, B, C, and D, and E. We work from left to right on a line from the random number table and go, okay, let's assign a plot to treatment A first. So we have plots 1 to 5, so we find the first occurrence of the number 1, 2, 3, 4, or 5 from the table and assign treatment A to that. Then we go to treatment B and find the next number that we haven't used that appears on the random number table and do that for all 5 of our treatments. In reverse, we could go, okay, we've got 5 plots, I'm going to assign a number to each treatment and then work from one plot to the next, experimental unit to the next. So we might go, okay, let's look at experimental unit 1. Let's see what the first number between 1 and 5 that comes up is, and that will be the treatment that goes in that plot. Cycling is a technique where we only have a small number of experimental units, therefore we use the same number, different numbers to mean the same thing. So if we had 5 plots or 5 treatments here, we could assign the number 1 and the number 6 to the first treatment, and then for the second treatment we could assign the number 2 and the number 7, then number 3 and number 8, 4 and number 9, 5 and 0. Therefore we don't have to go as far along a line to get the occurrence of that number. So the first part of this audio/video ends here with a question. For this randomized block design, how many units are there overall? How many blocks are there? And blocks are indicated by sets of 6 units. How many treatments are there? And each treatment is given a number. And how many replicates are there of each treatment? Pause the video and have a go at that question. Now, so here the number of plots is or the number of experimental units is the number of small boxes across this entire experimental area, which is 6 by 4 by 4, which would be 96. The number of blocks is 16. The number of treatments is 6, and we've got 1 treatment would go into each block, so we'd have 16 replicates for each treatment. So the question now is what happens when we don't have this perfect arrangement where we have a perfectly matched number of treatments for the number of experimental units in each block. If we do have this situation, we call it a complete block design. Every treatment is found in every block, and that is ideal, and that's what we should hope for, because it makes life a lot easier. However, if that isn't the case, for example, we have more treatments than we have experimental units in each block, or we have more experimental units than we do treatments in a block, then we have an incomplete block design. So we'll explore what happens in this situation now. So incomplete block designs rarely can be avoided for one reason or another, but if you think about it, you have to be quite lucky for your number of blocks and experimental units within the blocks to be the same as your number of treatments. So the next best situation we can have if we do have an incomplete block design is to have a balanced incomplete block design. And that is where any 2 treatments appear the same number of times together in a block, which means we always have the same number of opportunities, I should say, to compare the 2 treatments against each other. The main thing with incomplete block designs we need to remember is we need to maintain the randomization. So not only do we have to randomly assign treatments to experimental units within blocks, we need to take one step back as well and randomly assign subsets or groups of treatments to blocks, because not every treatment can be in each block, but we need to do this randomly. So we're going to look at a couple of examples which require you really to sit and go through them yourselves, but I'll explain it, or attempt to explain it in my own words. But the notes are quite self-explanatory once you give it a little bit of time to sink in. Also, the questions set on the subject homepage are also very useful for this. Let's look at this first example. We want to test 5 different methods for hardening the hooves of sheep. So the best case situation would be to have 4 treatments to test, and we'd test each one on a sheep at the same time. We'd randomly select a hoof on each sheep and apply 1 hardening treatment to each hoof. Then we'd be able to compare it on every sheep. That would be absolutely ideal because we'd be removing sheep to sheep variation. But as it stands, we have 5 treatments, and sheep don't have 5 legs. So somehow we need to assign groups of treatments to different sheep. So we've got 10 sheep, which means 40 experimental units overall, because each sheep has 4 hooves each. So we have 5 treatments, 40 experimental units. 40 divided by 5 gives us 8. So we've got a possible of 8 replicates for each treatment, which is pretty good. So somehow we need to randomly assign groups of 4 treatments. So if we're doing groups of 4 treatments, and there's 5 treatments overall, then that means that each treatment is going to miss out on a sheep twice. If we randomly divide them up and make sure each treatment gets as many replicates as possible, each treatment will miss out on 2 sheep each. So somehow, pardon me, we need to randomly assign which sheep each treatment is missing out on. In other words, find 2 sheep that each treatment is missing. So we do this using a random number table again. Here we've got an excerpt from a random number table at the top. So we go from one treatment to the next and find which sheep that treatment is missing from. So let's say we've got sheep 1 to 10. So the first 2 digits between 1 and 10 that we find will say treatment 1 is missing from that. So moving from left to right, the first 2 numbers are 3 and 7. They fall between 1 and 10. So we'd say that treatment 1 is missing from sheep 3 and sheep 7. So treatment 1 would be found on all the other sheep aside from those 2. I should point out, so where do you get the 10 from? 10 in this case will be 0. So wherever a 0 comes up, that would be sheep 10. Treatment 2, we just move along the line and find which 2 sheep treatment 2 is missing from. So the next number is 6, so it'll be missing from sheep 6. Then the next number is 7. We've already got treatment 1 missing from 7, so we move to the next number, that's 1. So sheep treatment 2 is missing from sheep 1 and 6. We do this for the rest of the treatments and we find the 2 sheep that each treatment is missing from in turn. In this example here, and the exact details aren't important, but you can take the time to read them. We have 5 treatments, however 6 experimental units in each block. So it's the reverse of what we had before. We've got more experimental units than we have treatments, whereas before we had more treatments than we had experimental units. So in this case simply, we need to randomly assign one treatment to be the extra one in each of these blocks. And we do that for treatment 1, for block 1, 2, 3, 4, and 5. Find out which treatment goes in each, and then, so we know then that the 5 treatments are going to be in each block, and then that extra one, and then we'd randomly assign a position for those within each block. When we have two blocking factors that need to be taken into account at right angles, we use what's called a Latin square. And Latin squares are like the Sudoku of experimental design. What we do in a Latin square is we have each treatment only represented once in each row, so left to right, and once from top to bottom. We do this by multiple layers of randomization, which is fairly simple when you go through it. The first step in a Latin square is simple. We just put each treatment in a row from the first to the last. So in row 1 we have A, B, C and D. And then for the next row we just push each treatment along one column. So treatment A goes from column 1 to column 2, B goes from 2 to 3, C goes from 3 to 4, and D goes from 4 back to 1. And then for each row below we move it one spot over. This is the start of our Latin square. Alright, so we're in a very non-random situation at the moment because we just did this easy A, B, C, D in the top and then moved them one step to the right each time. Not random. So what we need to do is reorder these rows. So we get a line from the random number table to start this off. And in this example we're going to be switching rows around. So there's 4 rows. So we're interested in numbers between 1 and 4. So we don't have to move too far along the random number table. We'll be using that cycling. So 1 will be represented by the number 1 as well as the number 5. 2 will be 2 and 6. 3 will be 3 and 7. And 4 will be 4 and 8. So we start with the first row. Where are we moving the first row? So we start from left to right on the random number table and look at the first number. It's 3. So row 1 will move to row 3. Then row 2, we move to the next number, 7. And remember 7 is the same as 3. 1 is 5, 2 is 6, 3 is 7, 4 is 8. So we can't use 7. The next number is 6. 6 is the same as 2. So row 2 would stay as row 2. We go to the next, again we get a next number 7, we've got that already. The next number is 1. So row 3 goes to 1. And then by process of elimination, row 4 goes to 4. It's the only row left, so it stays where it is. So we've now randomly switched around the rows. Now we need to do the same for the columns. So here we have another Latin square in action, using with 2 blocking factors, nitrogen level and moisture. The question is which one best accounts for both of these blocking factors? Well, we'd want a Latin square because we're trying to take into account 2 blocking factors, and you look at design A, remember there has to be 1 treatment in each row and column. In design A, straight away in the first column there's the control treatment, none and none in the same column, so that wouldn't work, whereas design B is a true Latin square. So in this subject we now move away from experimental design and move into inferential statistics, which is testing sets of numbers. We've described sets of numbers, now we're going to start testing them. It's a really exciting thing to study and very, very useful. I'll leave this discussion of experimental design with 2 slides which have a set of general rules for when to use each type of experimental design.